So let's look at the trig functions and their inverses. We'll start off with sine. So here's what our sine function looks like. And remember, when you invert, you flip the y's with the x's. So the inputs become outputs, outputs become inputs. And in order to be able to invert, you have to pass the horizontal line test. Notice there's lots of places where sine will cross this horizontal line more than once because of its periodic nature. So sine is not invertible because we would have multiple inputs that have the same output, which when inverted would mean an input with many, many outputs. So we have to restrict sine in order to invert it. So we'd like to take a chunk of this curve that would pass the horizontal line test. Well, ideally we'd like to go the full range from -1 to 1. So we could go from a valley to a peak or a peak to a valley, anywhere we like. But this first little chunk is the first quadrant, 0 to pi over 2. So we'd like to include the first quadrant. So this valley to this peak works the best, and whoops, that's what we define it as. So let me thicken this up a little bit there. So that from -pi over 2 to pi over 2 is the piece that we're going to invert. Because if I just look at that, let's turn off the sine. Now, here's just that little bit. That thing will pass the horizontal line test. It is invertible. So remember, when you invert, because you're interchanging your y's with x's, the inverse ends up being a reflection across that line y equal x. So if we look, there's what sine inverse looks like. The black curve there is our sine, and the red is its inverse flipped around there. They both exist over a finite domain and range. So for us, they're not very interesting for some of the stuff we want to do out to infinity because they only exist for a finite amount of time there. Okay, cosine would be similar in that cosine is not invertible either. It fails a horizontal line test as well. I'm going to be able to draw a line that crosses that many, many times. So that's no good. But again, we would like to restrict ourselves to some span of cosine that goes all the way from its lowest to its highest, or highest to lowest. But we'd also like to include our main reference angles in quadrant 1 of 0 to pi over 2. So the thing that makes sense would be to start here and run down to the bottom. That way we include there and are still invertible. So that's the piece that we restrict ourselves to. That piece right there. And so let's think about the inverse. The inverse will be a reflection along that line y equal x. And so there's the mirror image. If we flip that, we get something like that. Cosine runs from 1 to -1 vertically. So now horizontally, this is -1 and 1. Vertically, this inverse is 0 to pi, where this one horizontally is 0 to pi. Okay. The most interesting one, I think, is tangent because, let's take a look, turn that off. Again, just like all the other trig functions, because of their periodic nature, they are going to fail a horizontal line test many, many times over. So they're not invertible. So I'd like to take the full range here of tangent from -infinity to infinity. So I could take any one of these pieces between asymptotes. Again, the logic is we'd love to include 0 to pi over 2. So the one that makes the most sense is to restrict yourself from -pi over 2 to pi over 2. So we'll take that one piece right there, turn off the rest. Now, what would the inverse look like? it's going to be the reflection of that curve over the line y equal x. Now, the reason I said this one's interesting to me is that the inverse now, unlike sine and cosine, this inverse extends all the way to positive infinity and negative infinity on the x. And it's got asymptotes, horizontal asymptotes, where the other one had vertical. Tangent has vertical asymptotes at pi over 2 and negative pi over 2. Tan has them at pi over 2 and negative pi over 2 horizontal. So if you take the limit of inverse tan all the way out to positive infinity, you're going to run up against pi over 2 there. That red line is the horizontal asymptote. So let's turn off tangent and y equal x for a second. Just focus on the inverse tan. So there's inverse tan. So out at infinity, inverse tan's approaching pi over 2. And at negative infinity, it's approaching negative pi over 2. So not only does its limit exist both ways, it's an interesting number. It's not just 0 like a lot of our functions when their limit exists at infinity. And it's different depending on which way you go. Negative infinity, you get negative pi over 2. Positive infinity, your limit's going to be pi over 2. So the thing to keep in mind when dealing with inverse trig functions is they've got a limited. The trig function had its domain limited when we inverted it, which limits the range on those. So tan inverse here is between negative pi over 2 and pi over 2. If we look at cosine inverse, it's between 0 and pi on its range. And sine inverse from negative pi over 2 to pi over 2 on its range.